in waves and seconds. But at the moment it's very fashionable again to sort of look at warm dark matter. And sort of if I sort of introduce the free streaming and the properties of the dark matter that affects the power spectrum on the relevant scales, I can make these small halos vanish by them just not never collapsing because they're not present in the power spectrum in the first place. At the same time, it makes these somewhat larger halos that are still present more fluffy because they form later when the universe has a smaller mean density, and as the sort of the halo structure reflects the density and then they collapse, they become more fluffy too. In principle, that is a very elegant way of solving lots of these problems. Unfortunately, I think we have good measurements where we can rule out the interesting part of parameter space for this. So what we do is we don't look at this high nonlinear phase of the models. We look at the columns clumps, and there things get much more difficult. The line alpha forwards, we can look at the power spectrum on the same scales before the gas has fully collapsed. And what you see is what the free streaming of the gas does to space, we just relate the structure. While this model, the structure is sort of given by the resolution of the simulation. You see the simulations are under the same resolution and nevertheless it's much less smooth scale structure. This is sort of for very large free scaling lengths. But there's a lot of structural erase just due to the fact that the dark matter here is cold, but it's sort of what's called warm. So the effect on the line alpha forwards that has is shown here. Sort of for here's the free streaming length. It's a physical quantity that's actually measured in this way. It's parameterized by the mass of a thermal relic, and sort of you have to be careful if some people quote warm dark matter masses because it's not a thermal relic, so it becomes a complicated relation, and there's a lot of confusion as to the fact what mass is actually meant. The physical quantity is a free streaming length, and you can take the mass as equivalent. The higher the mass, the closer it gets to lambda CDM. We see the noticeable differences in how the line alpha force looks like, and you can sort of quantify that by taking a Fourier transform of this and look at the power spectrum. In this way, you get nice constraints, and the nicest constraints you go by looking at the smallest scales. Actually, what you need for doing that well is a nice sample of high resolution spectra. And here's sort of a sequence in redshift of what's called the flux power spectrum. This is the Fourier transform of the flux distribution. Here's the Sloan data with a wide range of the redshifts. And here's a high resolution sample. And the real constraint from the smallest scales is the highest redshift. Turns out pushing to higher redshift is actually most favorable to test the smallest scales for this. And there's where you can look for the cutoff in the power spectrum. And we're doing that game now for 10 years or so. And this is our latest, and this is more and better data with better simulations. And we really looked at the systematic errors, put a lot of evidence, and the one who's actually leading that and whose work that maybe is Matteo Beal. And sort of we are sort of doing all the line alpha forwards together, but the warm dark matter stuff is sort of really led by Matteo Beal. So the constraint in the end gives you a mass that you can quote in terms of a thermal relic, and it will show just in a second the plot what that means for what you're more interested in, what it means for dwarf galaxies. And so the model that has been discussed a lot, what actually has a significant impact on how much small scale structure there is a 2 keV model, but that's clearly ruled out. But this kind of data you see sort of already showed in the kind of small scale structure that you have. Sort of the data actually once that the universe is lambda CDM all the way down to the way they can actually measure this method. So the limit is sort of 3 keV and a 2 sigma confidence level after we sort of had been as critical as possible with the systematic errors and turned it with stone we could. So what that means is that dark matter is what I call pretty cold. And this morning we had sort of said that it's interesting that it becomes at 10 to the 10 solar masses, and you basically stay cold for at least another 10 to 30 in mass. And sort of at that range, you will not establish that you're really CDM to the limit, for example, what a wind would do, but it sort of starts to become uninteresting for galaxy formation because you go to so small halos where you're really convinced that the baryons really take over and see what's happening in them. If you want to ever do better on this, you have to get to cooler gas, and maybe in 20 years you can do set better with 21 centimeter emission. So with this method you will not push it much further because you're running into the thermal in the gas power spectrum. This is a paper where I like the title very much. I checked the title, didn't actually make it as a published version. The referee obviously was the editor, wasn't happy with it. It's me by code differently. But what you see here is that if I make the mass small enough, the free streaming length large enough, it actually does exactly what you want. It makes the things more fluffy. And you could solve the too big to fail problems this way and having more fluffy halos and having fewer of them. For the masses that are still allowed, it's pretty similar code to code that matter. And I think this is sort of my stand on what you can do with a line alpha focus on warm dark matter. And these constraints are sort of fully marginalized over cosmology. So it's not like if you try to do that with the number of satellites that you basically don't quite know what the mass of the Milky Way is, and on that is really fully marginalized over all parameters. What's at the heart of this is actually excellent data, and you have the local expert here, Jason Bohaska, who sort of has data sets like this and even larger too. This is based on what George Becker sort of has in his drawer, and this is just large samples of very good spectra of Keck spectra, and you know your best how expensive to get these large samples. And what's equally important is that you model these spectra well. So this is two examples where we actually looked at the proximity effect, but here you see to which lengths we gave to model these spectra. This is always an observed and simulated spectra. And with the simulation you can model these really well, and that's really good quantity constraints. And this is sort of it's not the latest sample that George has, but he sort of he's inherited whole Sargent sample and got quite a bit more. So there's actually a lot of data was actually going into that too. So that was sort of what I had said so far was on dark matter. Now I want to go into physical properties of the IGM and say first a little bit about the thermal state of the IGM and what kind of measurements we have there. So the first to discriminate that from what we did on the warm dark matter, you might think sort of if the dark matter is sort of has a temperature on its own, is warm, how discriminate, or how well can I discriminate that from actually having a thermal temperature of the gas itself. So this is the flux power spectrum relative to a CDM model for cold and a hot model and the warm dark matter model. And you see even so the effect for basically becoming cold and becoming hot and having warm dark matter is similar, but it's very distinct. So sort of given the quality of the data, you can easily discriminate the two. There's a different redshift dependence, there's a different scale dependence. You can at the same time actually, up to certain limits, when you really get into the thermal cutoff, you can at the same time get good constraints on the free streaming of the dark matter and measure the temperature of the gas as well. So measuring the temperature of the gas is sort of a tricky disease too, because there isn't sort of a temperature. Sort of in the simulations there's certain simplifications as well, but even after this simplifications, I think there's a wide spread of temperatures, and there is a sort of a tight relation between temperature and density. So the temperature in most of the simulations is rising as you go to higher density, and that's the balance between adiabatic cooling and photoheating that establish it. This changes with redshift 2, but you sort of have to decide at which density you actually measure the temperature and talk about it. So normally people normalize to mean density, but you don't quite know where mean density is if you look at the IGM, and sort of you have to correct for this, and this is sort of part of the tricky part of the business. The other thing, just as a warning, if you're running these kind of simulations, I think things are getting good enough that you have to worry now about actually running a non-equilibrium solver for your chemistry, because doing helium ionization, hydrogen ionization starts to make substantial differences. And sort of this is our best on the temperature measurements, and that's led by George Becker, who sort of after 6 years in Cambridge has just unfortunately left us now to a permanent position, not unfortunate for him, but unfortunate for us. He's just moved to Space Telescope Science Institute, and what George has done, he has done carefully at the same time measure the temperature of the Lime alpha forest, looking at the curvature and the flux distribution, and measured, sort of calibrated by numerical simulations at which density actually has measured the temperature. So the nice thing is here he gets the temperature measurement with very small error bars, but it's always at a different density, because as you go to higher sort of As you higher redshift, you're probing lower over densities, you're getting closer to the mean density, while at lower redshift, you're actually looking deeper into the halos, and that's just because the universe expand, the density changes. So if I want now to sort of put that into a plot where I have it all at mean density, I have to assume something about what actually the temperature density relation is. And this was a plot where he showed for two different values of approximating this temperature density relation as a power law, what kind of temperature evolution you get for the IGM at mean density, here sort of for a steep relation, for somewhat flatter relation. Independent of what we assume, we get a rise of the temperature, and the easiest interpretation was that that's the most plausible one that makes perfect sense. It's assuming that that's due to the helium heating doing helium ionization. So helium heating becomes more important until the helium mean free path becomes lower, the photons are actually not captured anymore because there's overlap with the helium regions, and then rises, and then the temperature starts to drop again. Sort of this was Rouge's temperature. Then there was another measurement that came out that sort of measured with the classical method of actually looking at the Doppler parameters of the line alpha focus from a student of Chuck Stridell, and she had fitted a very nice, very large sample of absorption spectra that were focused just at one redshift, unprecedented large sample of spectra at just one given redshift. And she got a nice measurement with small error bars that was quite a high temperature, and that sort of didn't agree with Rouge's for the gamma that she sort of measured at the same time. So she, on the lower cutoff of the Doppler parameter, she got a measurement of the slope of the temperature density relation as well. We have looked at that, and they didn't use simulation to calibrate that, and they sort of didn't calibrate that correctly. After we recalibrated that measurement with our simulations, we got the same temperature density relation, but the temperature dropped by nearly a factor of 2, and it now agrees very well for the same gamma. So there's sort of a very nice consistency, and I think we can claim now that we know the temperature of the IGM much better than even 5 years ago, and that we get really now here in the arm where we get to this small error. Sort of, can we model that? I think at the moment the measurements have become better than the modeling, because modeling the temperatures of the IGM is still a tricky business. And the reason for that is sort of at these accessible redshifts, helium ionization happens. And at that time, he makes a transition for helium photons from optically thick to optically thin. And that's a difficult business. And Sebastiano, as a student, has worked on that with a radiative transfer code, and that's sort of hard going. What most people have done so far, they use a simple 1D UV background model that your local colleague Piero Madao has sort of developed over the years, and that actually catches things amazingly well, given the simplicity of putting that together. And I think so far we are taking the approach that the temperature is still quite uncertain, so we had just a run with heating rates that we manipulated, and then afterwards it marginalized over a range of temperatures. But in this project, with the postdoc of mine, Ewald Kuchwein, we looked actually how well does this 1D model actually do, because in principle there's radiative transfer in. So there's a transition from optically thick to optically thin in. And I told Ewald, or at that stage we started with James Bolton on that after a long discussion with Piero. Let's just try how it actually does. It actually doesn't do too badly with the temperatures. One reason why we were skeptical before, because all temperature measurements were actually quite a bit higher. But now, sort of, if you take the same gamma that you get with the UV background, you actually are in the right ballpark. You have to be a bit careful that you actually put the non-equilibrium in. And things have changed going from the old Haehnelt out to the new Haehnelt out too. So the discrepancies here, and I will come back to that, but they're sort of not sort of as large anymore as it used to be. And strikingly, if we sort of correct for when helium ionization should actually happen to the Piero model, and that's not quite self-consistent what he does there. If you correct for that, and we have done that here, then you get here this purple line, and then you follow the observed temperatures actually very well. The method from that is that Haehnelt 2012, with some little tweaking, works actually very well for the temperatures. And if you put the non-equilibrium chemistry in, you actually have a very nice self-consistent, well, not self-consistent, but a model that's consistent with what we know about the observed temperatures of the IGM. So next thing I want to talk about is the ionization state of the IGM. So you can use the Lime alpha force that I've explained to calculate the ionization state. And what you do there is you measure sort of the mean flux level. Then you can use a simulation to turn that into a photonization rate, because you know for the bulk of the Lime alpha force it's photonization equilibrium, and you can actually work out what it is. What's at the heart of this is a good measurement of the mean flux level. And this is sort of some work I was not involved that George has done as well, and he sort of has improved that quite a bit too. So this is some older measurement here in these orange dots, and that's George's new measurement, take the power of the Sloan data, and he has a very good measurement now of the ionization state as well. That you can do from this kind of measurement of the effective optical depth. That's now done with very small errors. So if I measure the photonization rates, this is from older works that I did with my former student James Borton. You just use the fact that it's in ionization equilibrium. And if I assume something was a mean free pass, and that's what Jason has done a lot of work in and provided us with nice measurements of the mean free pass, the function of redshift, you can turn it into emissivity. And this is from a paper with Becker and Bolton that actually measures emissivity as a function of redshift. And this is exactly the emissivity that you need to end the ionization at 6. And again, Piero's model does quite well, and with a higher redshift, goes off by maybe a factor 2 or so, but I'm pretty sure Haehnelt 2014 or 2015 will get it right too, and then we're sort of one step further. What that corresponds to is this only 1 or 2 photons per hydrogen atom, and we have termed the term photon star utilization for that, would mean that you have to start early and nevertheless finish at redshift 6. So this is, if you take Haehnelt and look at the effective optical depth for helium and hydrogen, and the model does reasonably well again, taking into effect that actually helium ionization takes place here, and that's not sort of in the model explicitly, that's a fluctuation should become large here. There's some debate now with new data here that falls pretty low yet, but I've discussed it a lot with Mike Schall, and he sort of he is not convinced that that data is actually real. I think it would be hard to actually get something more so flat as the effective optical depth here with redshift. So I'm sort of start to side with Mike Schall here from helium too. On the hydrogen, it fits reasonably well too, and that's quite often a misconception that people think that POHS puts that into the model, that should come out right. But what he has taken is he has taken the observed column density distribution to model the opacity. But that's not quite the same as sort of calibrating the simulation. So this is sort of a success in a sense, sort of a hint how to improve it further of the model as well. So at high redshift there's a factor 2 discrepancy that you would see in the last one. At low redshift, the discrepancy might be quite a bit larger. And Pierre had a paper himself, Schooner Kohlmeier, was it turned out that there might be photons missing compared to his model. And this is sort of a space to watch as well. Sort of the last thing I want to talk a little bit about is realization. That's something where I put a lot of effort, and effort of the people I work with in. So sort of, as you know, we think realization ends with a redshift of 6. It's sort of the first stars and black holes produce photons, producing ionized regions, and then overlap, and it's sort of seen as a phase transition, and lots of effort is put into sort of understanding how that happens in detail. And George has sort of pushed that sort of on the observational side quite a bit with his latest paper, George Becker, and this paper just came out a month ago. This is from the talk just before it came out. And what he has sort of looked a bit into more is sort of not the meaning of the evolution of the mean flux level, but look a little bit more in detail into the fluctuations around that mean. And sort of the general understanding is as if you go to redshift 6 and 7, the effective optic goes up, but the scatter goes up a lot too. And we think that sort of the tail end of ionization, we have the overlap of the ionized regions. And with the mean free pass becomes comparable between the distance of the sources to the large fluctuations in the UV background. And George found one quasar here where there's a very large trough here that is not completely neutral gas here, but this is large optical depths over a large stretch, and you compare that to quasars at the same redshift, where there's actually the gas much more highly ionized, so there's no doubt that there's large fluctuations as we go beyond redshift 5. This is not new. I think Xiaofan has already found that in his sample. But what George has done now, he has been able, with this good data, to measure the effective optical depth even if it's large, and he can quantify now what the PDM of the optical depth actually is as a function of redshift. So he has produced basically these plots, that's the cumulative distribution of the effective optical depth as a function of redshift. And the gray lines are what you get using simple optically thin simulations. And while these fit very well at 3, 4, up to 5, I think as you go beyond 5, there's a clear deviation from that. And the nice thing is that George has well quantified that with that sample and with his collaborators. So there's clearly much more neutral gas as you would get in optically thin simulations. So that's something what you can really shoot at now with full radiative transfer simulations. That's what we're doing at the moment. So I've hired a young postdoc who has worked doing his PhD with the radiative transfer codes that you can process numbers with. And this is an optically thin simulation. This is putting self-shielding in. And this is sort of what there might be if you actually do it properly and you're not fully realized yet. We are now in the process of running these simulations, and what's key here is to run these really at high resolution so that you get the things of ionizing radiation well too, that you get the line of limit systems. And this is sort of just a glimpse of the work that we're doing at the moment, and the highest resolution simulations, here's the blue one, and this is here the probability distribution of the photoionization rate, and as you crank up the resolution, you really start to get these large fluctuations, spatial fluctuations of the photoionization rate. And we will now go after George's data, try to reproduce it quantitatively, and in this way we will learn a lot about what actually sources are, when it happens, and in what exact state of how much neutral gas there is and in what state we are there. So this is a very nice data set. So I'm at the end of 25 minutes, or then I just drop that and I'll show a summary slide and just start with a nice movie of our latest simulations where we took a lot of time on a big computer in France to do even bigger and quantitatively